Hello everyone, this is Mr. Appel, and today we're going to look at some special right triangles and the interesting relationships that occur in those right triangles. The first of our special right triangles is the 45-45-90 triangle, or the 45-45 right triangle. And those numbers you may be guessing refer to the angle measures. So in a right triangle, we have the other two angles 45 degrees. So what kind of a special right triangle is that? Well, we know if the angles are the same. The isosceles triangle theorem tells us that the opposite sides are equal. So we know it's an isosceles right triangle, and that's another way we can refer to it. So let's just say, for example, this side was A, and this side was B, and the hypotenuse is C. Well, we know the Pythagorean theorem applies because it's a right triangle. So we know that a squared plus b squared is equal to c squared. Okay, but in this case, we know that a and b are the same thing. So this is kind of a special situation. And so instead of b, I'm going to say a and a. And instead of a squared plus b squared, I'm going to say a squared plus a squared equals c squared. So now I'm interested in the relationship between a and c. Well, if I were to try this, let's try it with a number first of all and see if that doesn't make sense. So let's just say a is 5. So that means this side is also 5. So because it's isosceles, we can actually calculate the length of the hypotenuse. So let's see what happens. So if we do that, we get 5 squared, which is 25, plus 5 squared again, which is 25, equals c squared. So c squared is 2 times 25. So it's 2 times 25. And when I take the square root of both sides, what I get is the square root of 2 times 25, but the square root of 25 is just 5. So that becomes 5 rad 2. So when this was 5, and this was, when the two legs were 5, the hypotenuse was 5 rad 2. Well, an interesting thing happens. And let's go back and look at the general form here. So if I actually solve this equation for c, I have a squared plus a squared, that's 2a squared equals c squared. And if I take the square root of both sides of that equation, watch what happens. On the right, I get c. On the left, square root of 2 is still the square root of 2. But what's the square root of a squared? Well, the square root, I'm going to go off to the side, of a squared. The square root of anything squared, square root and square cancel each other out. That's just a. And so what I get is a rad 2. So what that means is, in this situation, I'm going to make a little bit of room here. Okay, that's better. So what that means is, if you have a 45-45-90 triangle, if you have these two equal, if the two legs are a, the hypotenuse is a rad 2. So now if I give you a right triangle, and I tell you that this side is 17, and that those angles are 45, those angles are equal, and I ask you to find the length of a hypotenuse, you can find it, and you can find it without doing any work, because the hypotenuse is just the square root of 2 times the leg. So if the leg is 17, right, which over here is a, the hypotenuse has got to be 17 rad 2. That's it. It's just that easy. So when you recognize these special right triangles, a 45-45-90 in this case, you can easily calculate. So let's just look at another quick example. I'm going to just mark it that way. That's still a 45-45-90, right, because I've got those two equal. And in that case, let's say this was 37 rad 2, and I wanted you to find the other legs. You could just work backwards and say those sides are each 37. Because again, if the hypotenuse is a rad 2, each leg must be a. And that is how you can use 45, 40, 90 triangles, or use those relationships to help you solve problems like this. All right, now let's explore the second of our special right triangles. This one's the 30, 60, 90 triangle. Now what I've done here is I'm starting with an equilateral triangle, and I recommend you draw this, and you'll see the connection hopefully in just a moment. So this is an equilateral triangle, so this is 60 degrees, this is 60 degrees, and of course that third angle up top is also 60. But let's see what happens if I drop an altitude down to the base. Well, we know dropping that altitude gives us a right triangle, and if we've got a 60, right, if this right here is 60, then this angle up here, each of those is going to have to be 30. So that's 30 and that's 30. And now what I'm interested in is the relationship between the hypotenuse. Let me just highlight. So I'm just talking about, I'm just going to pick one of these right triangles. Let me make that a little bit thicker. So let's say this right triangle. So this right triangle is a 30, 60, 90 triangle, because it's got a 30, a 60, and a 90. So let's just say the side of that big one was 10. Well, if this is 10, then this shorter side, this side over here, is, if you notice, it's half of the side, this side here of the big triangle. Well, what's the length of the big side? Well, the original triangle was equilateral. So if this is 10, this is 10, which means that this side must be 5. And so in a 30, 60, 90 triangle, the hypotenuse is always twice as big as the shortest leg. The shortest leg here is 5, hypotenuse is 10. Taking that a step further, wrong tool. There we go. Taking this a step further, if we use the Pythagorean theorem to find the length of the altitude, or the third side, or the longest leg, the longer of the two legs, if you went ahead and did Pythagorean theorem, let's just call this A, and you did, whoops, I don't know why I wrote B when I said A. Let's try that again, sorry. So we'd have A squared plus 5 squared equals 10 squared. I'm just going to quickly go through that. That's A squared plus 25 equals 100. That's A squared equals 75. And that's A equals the square root of, and I'm going to rewrite that as 25 times 3. We end up with 5 rad 3. And so that side ends up being the square root of 3 times as big as the short leg. Okay, so I want to try to bring all of that together now. So in a 30, 60, 90 triangle, the short leg, which is of course the one that's opposite the 30 degrees, so there's your 30 degrees, so this is going to be the short leg. If we call that A, let's say, I know the relationship between the short leg and the hypotenuse. The hypotenuse is double the short leg. And I know that the long leg is the square root of 3 times as big. So that's A rad 3. So if you know that relationship, you can then solve a problem like this. So let's make another 30, 60, 90. So we'll do the easy way first. Let's say the short leg is 7, and I ask you to find the lengths of the other two legs. No Pythagorean theorem needed here. You're going to know short leg to hypotenuse is double, so that's 14. Short leg to long leg is times rad 3, so that's 7 rad 3. It's just that easy. And the beauty is you can work in any direction. So let's just say, let me clear this out here. Whoops, all right, that's fine. We'll clear this out. Let's say I gave you that this leg, the long leg, was 10 rad 3. You could work backwards. So long leg to short leg is divided by rad 3, right? If we multiplied by rad 3 to go short leg to long leg to short leg we divide by rad 3. So that's 10 rad 3 divided by rad 3, and the rad 3's cancel, and we're left with 10. And then Short leg to hypotenuse is double, so that's 20. So with almost no work, we're able to determine the other two sides of the triangle. That's all for now. Thanks.